What do Saturn, the apparent motion of the sun, peanuts, and red blood cells all have in common? Cassini Ovals, and they're the key to solving today's midday mystery. During a recent late-night coding binge, I ran across this great question. Beta Panderetta asked, how can I plot a 3D lemniscate? Now, when I looked at the problem, right away I thought, well, this is a Cassini oval, actually. It's close to a lemniscate, but not quite. So, with Giovanni Cassini's 395th birthday right around the corner, I figured this would be a great problem to tackle. Now, we're just going to scratch the surface. I'll leave a link to more details about Cassini ovals if you're interested. And we're going to fly kind of quick, so hang on. To solve this problem, we're going to need a parametric equation. To get that, we'll start out with this Cartesian equation, which you can find scattered everywhere on the internet. Next, we build a polar version of this equation and solve for r. And then finally, we build our own parametric equation for Cassini ovals. Now, this parametric equation uses a subvariable m because it needs that part as a square root for both x and y, and it's just much easier to calculate at once. Notice here that our theta will range from 0 to 2 pi as we're calculating the different x and y positions in our parametric equation. So now let's just graph it. And note that our graph will change as we change the value of a. When a is 0, we have the standard circle. As a increases, we get an oval, and then eventually a peanut. And then eventually, when a is equal to b, or 1, we have the lemniscate. But in the question asked, it's not quite touching, so we'll back a up a bit to 0.97. And now we're back at our bone, or our peanut shape. But the user wanted a surface, so that means we have to work in 3 dimensions. So let's rotate the screen so we can see what this shape looks like as we rotate it in 3D space. Okay, so we realize we can make our surface by doing such a rotation. Now we have to figure out a parameterization to know what those different values are as we rotate it through the angles. So to figure out what that x, y, and z are, we'll start out with our x, y, and z from our 2D representation. In 2D, z is 0. And then we multiply that by a standard x-axis rotation matrix. When we do that product, we end up with this solution. So now we know how to calculate the parameters for any values of theta and psi here. We just need to put it into code. So our m is calculated. It's really just a copy of what you see here on the screen, but put into Python. Should make sense. And then we calculated our x and y. So notice I put the square root first on the screen, but the square root is second in the code. It doesn't make a difference. It's multiplication. Once we have our 2D, we can now calculate our 3D matrix. X stays the same, so we don't have to calculate that. But we do have to do z and y, multiplying them by sine and cosine respectively. And then we just simply return our matrix x, y, and z for our rotated parameters. Okay, back in our construct method, we create a boundaries dictionary. And then we create a parametric surface object, passing in our boundaries dictionary. And we set a specific resolution here. So you'll see a variable for that. The higher the resolution, the longer it will take to generate the graph. And then finally, I call the begin ambient function so we can see this shape rotate through space. And here's our result. Check out the links below to find out the many ways Cassini ovals are useful. And until we meet again, keep taming irrationality bit by bit.